Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from an Introduction to Mechanics by Klepner and Kolenko. Today we will discuss topics from Chapter 3, Momentum. So far we have been talking about motion of point masses and how to analyze the motion using Newtonian mechanics. So here we first identify various forces acting on the point mass, then draw the force diagram, write down the equation of motion, then we go on to solve it, right? So even if the system is quite large, if it is like an extended body, still we approximate it to a point mass because Newtonian laws are originally derived for point masses. But when you approximate an extended body to a point mass, are we oversimplifying things, or is there a scientific rationale behind this approximation? That's the first question. Now second, can we apply this Newtonian formalism to a system of particles? Right? Because most of the system which we see in our daily lives, these are multi-particle system or extended bodies, right? If you take a system of gas molecule, like 1 mole of oxygen molecule, it contains Avogadro number of atoms, right? There are large number of oxygen molecules. Similarly, if you take a piece of glass or a piece of silicon, it consists of crores and crores of atoms, and each atom you can approximate to a point mass. So basically you are dealing with a system of particles. Rarely we encounter a single particle system, right? Most of the time you have multi-particle system. Now, how do you analyze such a system? Let's imagine that we have a system of n interacting particles with masses m1, m2 all the way to mn and position r1, r2 all the way to rn. So this is a representative system consisting of 3 particles. So you have each mass characterized by its own position vector. Okay. Let's say the force on the jth particle is Fj and its momentum is Pj, where Pj is given by mj into Vj, where Vj is the velocity of the jth particle, or in terms of the position vector I can write it as mj rj dot. And the equation of motion for the jth particle is going to be Fj equal to dpj by dt. Force is the rate of change of momentum. This is same as F is equal to ma, right? Because P equal to m into V. Mass is a constant, so this is going to be m into dv by dt. dv by dt is acceleration a, so F is equal to ma. Usually when you have a point mass or a single particle system, you write down the equation of motion as F equal to ma. On the other hand, if you are dealing with a system of particles like the one we are talking about right now, we usually write the equation of motion as F equal to dp by dt. And the advantage of writing the equation of motion in terms of momentum, we will come to know about it very shortly. Now, the force acting on the particle, I can decompose it into 2 components. One is Fj internal, which is the internal force on particle j, and this is due to the forces exerted onto that particle by all other particles in the system. Then you also have Fj external. This is the external force acting on particle j, and these are the forces due to sources outside the system. Now, in terms of these 2 forces, I can rewrite the equation of motion as Fj internal plus Fj external equal to dpj by dt. So this is for the jth particle. Now, if you want to analyze the entire system, you have to write down the equation of motion for each of these n particles. So when you do that, you get this kind of a system of equation. So first one corresponds to equation of motion of the first particle, second particle, all the way to n particle. So if you are talking about 1 mole of oxygen molecule, you have Avogadro number of molecules there. For each molecule, you have to write down an equation of motion. So you are talking about crores and crores of equations. And if you want to analyze the motion of the entire system, you have to solve all these equations simultaneously this is going to be humanly impossible. Even for a supercomputer, this is going to be very, very difficult. So if you follow this kind of a sequential procedure, you are not going to reach anywhere. Now, you may be thinking, what if instead of dealing with each of these individual molecules or each of these individual equation, if I have a mechanism using which I can study the motion of the entire system at once, then that makes my life a lot more easy, right? So what do I do for that? So I take the summation of all these equations. So basically you have to take sum of each of these individual terms. So summation of over j fj internal plus summation over j fj external equal to summation over j dpj by dt, where j runs from 1 to n. Okay. Now let's see whether we can simplify this expression. So summation over fj external, this is nothing but the total external force acting on the entire system, right? So this is something which is measurable. So if I call the total force acting on the system as capital F external, then instead of summation over fj external in this equation, I can write just F external. Coming over to summation over fj internal. Luckily, from Newton's third law, I know that the forces between any two particles are equal and opposite. So they cancel each other, right? So if I have three particles like the one shown here, 1, 2, 3, the forces between m1 and m2, they cancel each other. The forces between m2 and m3, they cancel each other. Similarly, forces between m1 and m3, they also cancel each other. In other words, the forces between all these particles, the internal forces between all these particles, since they act in pairs, they are going to cancel each other. So the net internal force, summation over j fj internal, is going to be 0. So with these two, I can simplify my equation of motion for the entire system as F external equal to summation over j dpj by dt. Now from differential calculus, we know that derivative of a sum is same as the sum of derivative. So in other words, I can write summation over j dpj dt as d by dt of summation over pj. Now what is the meaning of summation over pj? This is nothing but p1 plus p2 plus all the way to pn, where p1, p2, pn are the individual momentum. So we are taking sum of all the individual momentum. This will give you total momentum of the system. You can call it as capital P. So with this, our equation of motion becomes F external equal to dp by dt. I hope you are able to appreciate the significance of this result. We are talking about a system of n particles. Originally, you will have to deal with n number of equations. You have to solve all these n equations simultaneously. N is a very, very large number. But now you need to deal with only a single equation, right? This equation characterizes the motion of the entire system. So your analysis is going to be much, much more easy now. So the total external force applied to a system is equal to the rate of change of the system's momentum. Now this is true irrespective of the details of the interaction. Your F external could be a single force acting on a single particle, or it could be the resultant of many tiny interactions involving each particle of the system. It doesn't matter. In either way, your equation is going to remain exactly the same. Now let's see what is the implication of this result in one of the practical situations. So let's take the example of bola. Bola is a weapon used by the gauchos. Gauchos are South American cowboys, and this is used for entangling animals. You can see it from this schematic. So it consists of 3 balls of stone or iron connected by thongs. Thongs are like strips of some cloth or leather. Okay. Now the gaucho rotates the bola in the air and hurls it at the animal. So what happens is mostly the legs of the animals get entangled between the thongs. So their movement is restricted. This enables the gauchos to capture the animals. Okay. Now what can we say about its motion? Okay, so hope you understood what is the purpose of using the bola. So now this entire story which I have described just now, we need to translate into the language of physics or into the language of classical mechanics. So from the point of view of classical mechanics, you have a multi-particle system consisting of three masses m1, m2 and m3, and the masses are pulled by the binding thongs and gravity, right? And for now you can neglect the air resistance, and since all these three masses are connected together, you can consider them as a single system consisting of three individual particles, right? So this is a multi-particle system. And if you want to analyze the motion of the bola, basically you need to understand motion of each of these individual balls. So you have three masses, you need to write down three equations of motion and you need to solve them simultaneously. But remember, since the constraining forces depend on the instantaneous positions of all the three balls, and the position very dynamically, even to write the equation of motion in this case is going to be really challenging. So if you go by a sequential method like writing down each of the individual equations and try to solve, it's going to be a Herculean task. On the other hand, we can follow the formalism we have developed just now. So you can write down the equation of motion in terms of the total momentum of the system. You don't have to bother about the individual masses. So the total momentum change dp by dt equal to F external, where F external is the total external force acting on the system. So here the only external force that is going to act is the gravitational force, because all other internal forces are going to be cancelling each other, right? So total external force I can write in terms of the external force acting on each of the individual masses as F1 external plus F2 external plus F3 external. And in terms of the mass, I can write it as M1g plus M2g plus M3g. If you call capital M as the total mass of the system, then capital M is going to be M1 plus M2 plus M3. So my equation of motion gets simplified as dp by dt equal to capital Mg. Now look at this equation. Even though we are talking about a system consisting of three particles, if you look at the final equation of motion, this is identical to the equation of motion of a single particle of mass m with momentum p. In other words, a multi-particle system you are simplifying into a single particle system, or a many body problem you are reducing it to a single body problem. So if you are talking about a many body problem, ideally you will have to write down the equation of motion corresponding to each of the particles, then solve the system simultaneously. As I said before, this is a very challenging task, but when you reduce it to a single body problem, basically you are writing down a single equation of motion which characterizes the motion of the entire system. So your analysis is going to be a lot more easy. Previously you had to deal with n equations, now you have to deal with only one equation. Now, how is this kind of a simplification possible? Or what is the scientific rationale behind this? That's the next thing we have to understand. Now, many of the time people use the concept of center of mass to reduce a many body problem to a single body problem, or a multi-particle system to a single particle system. Now let's understand what is center of mass. So if you recollect the previous equation of motion, F external equal to dp by dt, since all the internal forces cancel each other, the only force acting on the system is the external force. So let's get rid of the subscript external and just call it as F. So F is equal to dP by dt. And as I said, even though it refers to a system of several particles, this equation is identical to the equation of motion of a single particle. So if in fact this corresponds to the motion of a single particle, then I can also write the equation of motion as F is equal to ma, or F is equal to m into d square r by dt square, which is mr double dot. Right. Now we know that P is the total momentum of the system, which I can write as summation over j mj vj, or summation over j mj rj dot. Now if you club these three results together, I can write mr double dot equal to dP by dt, writing down P in terms of mj and rj dot. So when you take the derivative, this becomes summation over mj rj double dot. So mr double dot equal to summation over j mj rj double dot, or r double dot, or d square r by dt square equal to summation over j mj rj double dot divided by m, or r vector is going to be summation over mj rj divided by m. So r is a vector from the origin to the point called the center of mass. So if you take the case of three masses m1, m2, m3, the respective position vectors are r1, r2, r3. So in this case, the r vector, capital R vector, is defined as summation over mj rj, which is m1 r1 plus m2 r2 plus m3 r3 divided by capital M, which is the total mass, and this is going to be m1 plus m2 plus m3. So you have a point somewhere in the system, and the position vector of this point, or a vector from origin to this point, is known as the r vector, and this particular point is called center of mass. And the system behaves as if all the mass is concentrated at the center of mass and all the external forces act at that point. Now when you look back at the original equation of motion, what we have written here is nothing but the equation of motion of the center of mass. So even though your system consists of a large number of particles, you approximate it to a single particle system where the entire mass of the system is concentrated at a single point known as the center of mass, and you write down the equation of motion corresponding to the center of mass and you solve it, then you get the motion of the entire system. So using a single point known as the center of mass, you will be able to get the motion of the entire system. In other words, you are reducing a multi-particle system into a single particle system using the concept of center of mass. Now you can define center of mass as follows. Every physical system has associated with a certain point whose motion characterizes the motion of the system as a whole. Under the action of an external force, when the system moves, this point moves in the same way as a single particle with mass equal to the total mass of the system would move under the same force. Such a point is called center of mass of the system. Usually for uniform objects with regular shape, center of mass is going to be the geometrical center of that. For example, if you take a disk of uniform mass, its center of mass is going to be at the center. Or if you take a uniform rod, then its center of mass is going to be exactly at the center. So I can illustrate this with an example. Consider you have a system of two particles of mass 1 kilogram each. Now imagine that the first particle is situated at the origin, so distance is 0 centimeter, and the second particle is situated at a distance 10 centimeter from the origin. Now how do you calculate the position of the center of mass? we know this is going to be m1r1 plus m2r2 divided by m1 plus m2. So 1 into 0 plus 1 into 10 divided by 1 plus 1, which is 5 centimeter. So total distance is 10 centimeter. 5 centimeter is exactly at the midpoint. So if you have a uniform system, uniformly distributed system, then the geometrical center is going to be the center of mass. On the other hand, if you have a non-uniform system, suppose at one end you have 2 kilogram, at the other end you have 1 kilogram. Now what happens? The center of mass position vector capital R is going to be m1r1. This is 2 into 0 plus m2r2. This is 1 into 10 divided by m1 plus m2, which is 2 plus 1. So you have 10 divided by 3. This is 3.33 centimeters. So from the origin, the center of mass is at a distance 3.33. So you can see this is no more the midpoint. The center of mass has shifted towards the heavier mass as expected. Right? So that's about the center of mass. And if you take any system in our daily experience, it consists of a large number of particles. In some cases, the particles freely move around, like in the case of gaseous system. On the other hand, if you take a solid system like a piece of glass, then the particles may not be moving around because they are fixed to their relative position by strong internal forces. In any case, all the systems which we are dealing with is merely a system of particles, right? And even though the system of particles represent a complicated system in terms of analysis using Newtonian mechanics, you don't have to worry about solving individual equations of motion because the center of mass enables you to represent the multi-particle system in terms of a single particle system. And with respect to the external force, the body behaves as though it were a point particle. So basically, you write down only one equation of motion corresponding to the center of mass. You solve that equation of motion, then you can understand the behavior of the entire multi-particle system. Now, only one thing you have to remember here is when you write down the equation of motion of the center of mass, F is equal to mr double dot. Remember, this describes only the translational motion of the body. Translational motion means the linear motion, because this equation does not describe the body's orientation in space. On the other hand, if you are talking about rotational motion of an extended body or rotational motion of a multi-particle system, then you cannot simply write down the equation of motion in terms of the center of mass, because rotational motion often depends both on the shape of the object as well as the point where the forces are applied. So you have to make additional considerations when you try to represent rotational motion of an extended system in terms of center of mass. So that's for today. Thank you.